Hello, in this tutorial I will discuss the aldol reactions, example, mechanism, application to the natural product synthesis. The topic is covered in this tutorial: general reactions, mechanism, examples, application in natural product and total synthesis, and selectivity in kinetic and thermodynamic control of the enolate and ring formation. And what are the use in biotransformation, enzyme catalyzed synthetic reactions. So in biocatalysis, synthetic applications of the enzymes is discovered or discussed. So first we discuss on general reactions. So this is a general reaction with identical or different aldehyde also give the aldol reactions. So you can say two identical or different ketones or with keto or aldehyde. So this is a general reaction with the presence of the base, and with the two molecules combined here, and subsequently loss of the water molecule here give the double bond, and the stereochemistry is generally trans product is obtained rather than the cis. Sometimes both are the obtained. So basically reagents required for the aldol condensation is the NOH, barium hydroxide, potassium carbonate are generally base catalyzed. The aldol reaction can be catalyzed by the acidic medium or acid catalysis. Different extensions are also available for the aldol condensations, but general basic reagent is this. These are. Though why this is called aldol reactions? The product contain the both aldehyde and alcohol groups. So dehydration also is possible. So this is mainly addition of the enolate or enols to the carbonyls. So that's we discussed in the mechanism part. And two different carbonyl having the hydrogen, alpha hydrogen, like this one alpha hydrogen and this one is alpha hydrogen, give the cross products or self condensation give to the four possibility of the product. So we can eliminate the four product by taking the one molecule which is not alpha hydrogens. So this is the mechanism. First step is the catalyzing the formation of the enolate, which OH base abstract the hydrogen ions and leads to the double bond and negative ion on oxygen, which is nucleophile lovings. So the negative charge on oxygen is stabilizing this enolate. This is a formation of the enolate. And second step, the enol is attacking to the carbonyl system here. This is a electrophile carbon which attached to the oxygen. So these are the equilibrium reactions. So this is the condensation part, addition of the enolate to carbonyls, and next time the protonation of the alkylic side ion, which is formed by the addition of the products and give the products. Next is the dehydration steps is generally a subsequent loss of the water molecules. So this is the simple look of the mechanism, which is base catalyzed. Is similar to the acidic catalyzed mechanism. Now the next is the examples of the aldol condensations. These are the cross condensation between the aldehyde and ketone. Is sometimes called Claisen-Smith condensations. Generally aryl aldehyde with ketones, like the benzaldehyde with this is known as the Claisen condensation. You can say this is also Claisen condensation products, in which again trans chalcones is produced. So you see this aromatic aldehyde condensed with acetophenones and give the trans-chalcol the example of the Claisen-Smith condensations. If the one substrate having no alpha hydrogen, then it cannot condense self. So benzaldehyde does not have alpha hydrogen. This cannot be condensed with another benzaldehyde. With another special case, when that may be possible, but in simple carbonate like sodium carbonate, barium hydroxide, it cannot be condensed with itself. So it is not chance condensing the itself. So it can only possibility of the condense with itself. Acetophenones. The acetophenones cannot condense itself. There are a lot of reason, because the steric hindrance in ketone cannot condense each other. Second is the slowing addition to the uh, enolate ions. So these are possibility condition which lowering the self-condensation of the acetophenone. The other substance having alpha hydrogen self-condensation can control by adding it slowly to the substrate and base. So this is a again condition controlling the self-condensation of the acetophenone. First reason is the basically steric hindrance. Second is the addition, controlling the addition procedure. Slowly add, you can eliminate the possibility of self-condensation of the acetophenones. So two reasons: one is the steric, second is the addition conditions. So these are the example of the cross condensation. One is the aldehyde, another the acetophenone, one is the not alpha hydrogen. So this benzaldehyde condense with aromatic acetophenone and aliphatic aldehyde, also known as the Claisen-Smith condensations. The selectivity in cyclic products. Cyclic is the internal condensation of the ketones. So see this possibility of the 5-member and 4-member rings. So here is the generally 5-member is formed, not a 7-member forms. Okay, there's 5 and 6-member are formed because they are the stable less than 4 and 7-member rings. The 4 and 3-member are highly stable, but this is not formed. The 3 or 4 are not formed because they are the strain effect. The strain effect does not allow the 3 or 4-membered ring formations. Okay, that's the 7-membered is also not favored. So 5 or 6-member are mostly produced in the when the lot of options are available. Only 5 or 6-member are the allowed. Next is the selectivity of kinetic and thermodynamic controls. What is the kinetically or thermodynamics? When you add this position to this substrate, the abstract the less hindered hydrogen. So this is the most hindered hydrogen. So here the less hindered hydrogen, LDA is the hindered base, so it can abstract the less hindered hydrogen, leads to this kinetic control enolate and addition to the give this product. When the protic solvent OH, NOH or sodium hydroxide, this possibility of the both kinetic and thermodynamics controls. The thermodynamics leads to double bond have more substituted in this case. This is thermodynamics controls. So in kinetic control, less hindered is preferable. Here the more hindered is preferable. So this produce the thermodynamics stability of the enolates, and this leads to the thermodynamics controls which add the mixture of the product is obtained. So why this LDA has less substituted? Because they have steric hindrance base. Other ways for kinetic control used LDA, LTP, LHMDS. So these are the structures. Highly hindered base LHMDS. It's a highly hindered base, so it can subtract the here. The LHMD is the leads to very highly kinetic controls, which can abstract here, not here, because this is a less highly hindered, or this is a less hindered site. So this is the kinetic control and the thermodynamic control of the aldol condensations. So the applications of aldol condensation. You see the butanol is condensed itself, and reduction leads to mosquito repellents. So this reduction simple hydrogen alkyls. So now the citral plus acetone sodium ethoxide, which produce the intermediate of synthetic application of the vitamin A, which is leads to formation of vitamin A. The ester with the ketone give the 1,3-diketones. Here is like this one ester. Here the alpha hydrogen here condensed here. It's the 1,3-diketone, which is synthesis of the nicotine. Similarly, transchalicone, which is flavonoid in conditions. So here the chance is the the alpha hydrogen, which is abstracted and reacted with this aldehyde, gives the transchalicones, which leave the flavonoids. This example of the natural product synthesis. So this is a condensation of the internal condensation, taking here the five-member rings formed and reduction to the cis-Jas-main group is obtained. Similarly, another example, the carbon is synthesized also aldol condensation products. Acron also produced by the internal condensation products. So what is the biological aspect of the aldol condensations? The aldol condensation enzyme, which is used in glycolysis, also use the aldol condensation product. One is the ship-based mechanism-based classification with ship-based formation and zinc-based enzyme, which catalyze the aldol condensation. The fructose 1,6-diphosphate FDP aldose is separated from the rabbit muscles, is commonly known as rabbit muscle aldols. Raman is used for the condensation reaction. This FDP is is glycolysis, reversible condensation of the dihydroxyacetylphenols and glycerol 3-phosphate leads to the 6 members, 6 carbon aldol reaction. This can reversibly catalyze the condensation. What are the synthetic applications? I will show the next slide. The synthetic applications. This is a 2-deoxyribophosphate aldose is catalyze the condensation of the acetaldehyde with glyceraldehyde in biotransformation enzyme for the synthesis of the many molecules. So this is a synthetic application of the enzyme which catalyze the desired product, highly selective, highly favorable, highly kinetically controlled, or you can say highly stereoselective enzymes. So in biotransformation, the enzymes are the more efficient than chemical catalysis because they are very selective substrate, they are very selective stereochemistry. So many substrates, many molecules are synthesized by the enzyme thereof, which catalyze the condensation of the two molecules with highly stereospecific value. So this is a biotransformation application of the aldol reaction enzymes in synthetic application and synthetic chemistries. So this is all about the aldol condensations. So these are the topics covered by the aldol condensation. Please like and subscribe my channels. Thank you for watching.